everyone to today's TEOS seminar. It's a great pleasure to welcome Dr. Jennifer Francis from Rutgers University as today's speaker. So I would like to tell you a few things about her background. She studied meteorology for her undergraduate degree at San Jose State University in California. Then for her PhD, she went to the University of Washington, where there is a very highly rated atmospheric science program. And her PhD research was on satellite monitoring of polar climate or Arctic climate. And soon after her doctorate, she joined the Rutgers University in their Institute of Coastal and Marine Sciences, where she is now a research professor. So Dr. Francis is a recognized leader in the field of polar research, and she is a member of the Polar Research Committee of the National Academy of Sciences. And so as all of us know, the changes due to greenhouse warming are the most rapid at high latitudes in the Arctic region. And then Jennifer Francis has a very interesting theory that links that warming in the polar region to extreme weather here in mid-latitude. So she can explain why in a warming climate we can have periods of intense cold weather, for instance. So let us welcome Jennifer Francis.
Thank you very much, Sultan. Can you all hear me okay? Sounds pretty good. All right, well, thank you so much for inviting me to be here. I've never been to Stony Brook before. This is my first time, but I have a very good friend and colleague at Rutgers who I know graduated from here, Bob Chant, who many of you may know. And he and I kind of had our children exactly the same time, and we were going through the pains of early parenthood together. So we share a lot of both scientific and personal.
It gets worse.
No, it's just awesome. We got teenagers now, and I'm happy to say that they're awesome. So anyway, I'm really happy to be here and to visit this part of the country, which I've actually never been to before. So I'm going to be talking about a paper that we wrote earlier this year, and I'll review some of that work first. But more important, I want to talk to you about some new stuff that I've been doing, and you're the first people I'm telling about it. So I would really like to get a lot of questions, a lot of feedback. If you tell me I'm out to lunch, I want to hear that too. So please, let's make this more of a discussion, and if you have a question, please ask it at any time. So let's start by looking back to the good old days when we could look down on the top of the Earth and see this beautiful, thick cover of ice on the Arctic Ocean. This is back in 1980, only 30 years ago. And you can see here's Greenland and North America on the left, Siberia on the right, and all that pink and red stuff is sea ice at the end of the summer. And you can see how it pretty well fills the whole Arctic Ocean. But as we know, this is not the case anymore. Back in 2007, only a few years ago, the sea ice looked like that, which is about 40% lower or less ice than it was only in 1980. And of course, just a few weeks ago, we smashed that record that happened in 2007. We're now looking at an ice cover that is about half what it should be during the summertime. I mean, it's just mind-boggling in my opinion. And not only is the ice much smaller in extent in how much real estate it's covering, but if you can see the colors there, they're not as deep pink and purple as they are over here. There's more reds and yellows. That's telling us that the ice is very mushy and broken, and it's not healthy ice anymore. It can be very easily blown around by the wind and melted by any anomalies of heat or whatever. So things have changed so much. As I said, about half of the ice has been lost in only a period of about 30 years. This is just incredible. And the ice that's left is very, very vulnerable to any anomalies in wind speeds, in wind directions, and heating. So let's just talk about how unusual this is. So we can look back in time pretty well to back into the late 1800s even, and the ice records, this is a measure of ice extent on the vertical axis and time on the horizontal axis. You can see that going back to about the late 1800s, the ice wiggled around a little bit. This is the summer extent, but it was pretty steady. But something happened in around the 1950s, and we know what that was. The greenhouse gases started to increase as a result of burning fossil fuels after the Industrial Revolution and World War II, and the ice started to decrease in extent quite dramatically. And if we bring it up to closer to present, you can see that that trend is actually accelerating. And if we put this summer on there, it's just another huge drop in this record. So this is really incredible. And in fact, we can look back in time even farther. This is a new paper that came out by Christophe Pinard, looking at proxy records of ice extent, using things like tree rings and sediment cores and things like that, going all the way back almost 1,500 years. And yes, there's a lot of uncertainty in the signal, but what you can see is that even over this whole period, I don't know if you see my little arrow, there we go, it wiggles around year to year, but you know it's pretty steady. And then superimposed on here in blue is the recent record, and you can just see how much is dropped compared to the distant past, as best we know. And then once again, you put this year's ice cover on there, and it's just amazing. So it's not just about ice extent, it's also about the actual volume of the ice. And what we can tell from this research done at the University of Washington, where they actually take the reanalysis weather information and they drive an ice ocean model with it, and using that they can estimate the ice volume in the Arctic. So what we've got here is the annual cycle from January to December, and the ice volume on the vertical axis, and you can see as this marches through time over the satellite record that the amount of ice volume is also decreasing dramatically. And there's this nice little animation here that I wanted to show you that I think really visually gives you a pretty good idea of what's been happening in the Arctic. And let me just tell you what you're looking at here. So you've got Alaska, Greenland, and Siberia up at the top. And what this is an estimate of ice age. And the way this is done is with satellite imagery, tracking individual features in the ice and watching them over time and keeping track of how long they've been there and where they're going. So the white stuff is the oldest ice, 8, 9 years old. It's been circulating around in the Arctic Ocean. And as you get up into the bluer colors, it's younger and younger ice. And ice age is directly related to its thickness. So old ice is thick. Young ice is very thin. So what you're going to see here as the animation progresses is a pulsing of every year. So every winter the ice grows, and then every summer it shrinks. So you're going to see this blue stuff coming and going. And then you're going to see some motion in the center of the winds blowing around these pieces of ice. And as we march through time, what you're going to see is this white stuff, the very thickest ice, gets exported out into the Atlantic, which is the typical pattern that it takes. But starting in the 1990s or so, which is where we are now, you can see that the white stuff is starting to really drop. There's much less of it now. There's much more of the thin blue ice, especially important in the summertime. And as we get up closer to the present year, there's 2006, you can see we're losing more and more of that thick ice, and it's just being exported and melted right out of the Arctic. And I'll freeze that right there. You can see what we're left with. This was last year, but it's amazing how much less thick ice there is. So that just goes along with that volume change, much less ice. All right, so why is the ice disappearing? Well, okay, so we have this record, this time series down in the corner there showing the ice anomalies going back to the late 1950s. Remember I said it was really starting around the late 1950s when the ice really started to disappear. And that is again showing what it looked like back in the good old days. So as we added greenhouse gases to the atmosphere, the ice gradually got thinner and thinner. And then in the early 1990s, there was a period when the Arctic Oscillation, or the North American NAM, North American, what's it stand for?
Northern Ireland Mowers.
Mode, sorry, yeah, Northern Ireland Mode. Went into this positive phase for several years in a row, and this flushed a lot of the thick ice right out into the Atlantic, and so we're left with this thinner ice cover because of greenhouse gas warming. It can't recover because it's so thin now that it's very vulnerable, as I said, to any anomalies in winds or heating, and so we find ourselves falling down this path, and we're left with much more open water than there used to be. And all the energy from the sun during the spring then goes into these areas that are now open water that used to have ice on them. When it had ice, most of that energy from the sun would be reflected right back out to outer space. But now that energy is going into the ocean, warming the ocean, and then it has to be re-released into the atmosphere when the fall comes. So that's what happens, all that heat that gets absorbed. This is probably exactly what it looks like up there right now, because we're right at the end of the melt season. We've reached the minimum for this year, and so now all that heat that was absorbed over the summertime in the ocean is now having to get back up into the atmosphere in the form of sensible heat, water vapor, and infrared radiation.
Yeah, I have a question about
Yeah.
sort of this subject. Isn't the polar region in summer actually covered by low clouds, and so a lot of the radiation is actually reflected back by the clouds anyway?
It is, but a lot of radiation still does get to the surface, and the clouds are increasing somewhat because of the loss of ice and the more availability of water evaporated from the surface. But the cloud change is not that big relative to the albedo change of the surface. And so there's still a fair bit of solar energy that makes it through the clouds and does get into the surface. So we're not changing the medium that it's passing through, but we are changing what's happening in the surface. So, and there are breaks in the clouds too. So there's plenty of solar energy still makes it through the cloud. So as a result of all this extra heating that's getting into the Arctic Ocean, what we see if we look at the temperature anomalies across the globe is that over the last decade, we see the warming happening much more at high latitudes than we do anywhere else on the globe. In fact, it's about twice as much. This is the annual mean temperature anomalies, and if we look at winter, they're even larger. And notice that the scale is quite a bit larger. So we're seeing a lot more warming going on in the Arctic. This is what we call Arctic amplification. So the idea then is we've got all this heat going back into the atmosphere in the fall and the winter, mostly in the fall. How is it going to affect the atmospheric circulation? It's hard to imagine that all this energy would not affect the northern hemisphere circulation in some way. And in particular, how is it going to affect maybe even extreme weather in the northern hemisphere? So the kind of extreme weather that I'm thinking of is the type that's caused by weather patterns that move very slowly. So I'm not talking about hurricanes, I'm not talking about tornadoes. It's things like droughts. If you have a few sunny days in a row, everybody loves that, it's not a drought. But if it goes on for weeks, or a month, or 2 months, then all of a sudden it's a real problem. And a cold spell, if it's a few days, no problem. But if it goes on for weeks, then it becomes an extreme event. So it's these kinds of long-lived weather conditions that we're calling extreme weather here. And we can look back at cases, and in fact, this is a composite of the coldest days in Tampa and the 500 millibar pattern that goes along with that. And you can see that the kinds of extreme weather that we're talking about tend to be associated with very high amplitude flows in the 500 millibar field. Here's an example for, again, the coldest days in Tampa, where you've got a great big ridge over the western half of the country, a big trough over Florida, and that's what brings extreme cold events to Florida. Or the hottest days in Atlanta, same kind of thing, a big ridge parked over the middle of the country with big troughs on either side, very high amplitude pattern. The wettest days in Chicago, we have this big trough parked over the Rocky Mountain area with a big ridge over the East Coast, just sucking moisture right up into the Mississippi Valley and Chicago area. So these are the kinds of patterns that tend to lead to some kinds of extreme weather events. So these are the kinds of things that we're looking at. All right, so let's focus in on the fall, which is when all that heat starts to get released out of the Arctic Ocean and goes back into the atmosphere. And we'll start by just a mean 500 millibar height field for the last 12 years. And you can see what you'd expect here. Because it's colder over the Arctic, you see low heights over the Arctic surrounded by the strong gradient in the 500 millibars, with a trough sticking down along the east coast out to the Pacific and maybe somewhat down over Eastern Europe. Now, if we look at the thickness anomalies, the 1,000 to 500 millibar thickness anomalies that go with this time period, and these are all from MSEP reanalysis, by the way, what we see is these red colors are positive thickness anomalies in response to all that heat that's coming out of the Arctic Ocean because of the ice loss. The white asterisks are where the anomalies are significant at the 99% level. You can see this big area covering the whole Arctic region where the anomalies are positive. So what this means is that if you think about the gradient between the Arctic and latitudes farther south, this is going to weaken that thickness gradient. It's going to weaken the flow at the 500 millibar level because you don't have as strong a gradient anymore, and in some places more than others. So in the paper that we had earlier this year, we focused mainly on North America and the North Atlantic. So I'm just going to quickly review some of that in this particular area and look at the kinds of effects that we'd expect to see because of this weakened poleward thickness gradient. So one thing we'd expect to see, as I already mentioned, is this gradient weakening, and that's exactly what we're showing here. These are measurements of the difference in thickness over all 4 seasons. The brown one is the fall here, and you can see a definite decrease since the early part of the record, and also in the winter time. And even an indication that it might be happening in spring and summer as well. And with that, you'd expect to see a decrease in the wind speed, the west to east wind speed, the zonal wind. And this is also what we tend to see. So October over this region is in brown there, and wintertime in blue. And the fall decrease is approximately 15% over the North America, North Atlantic region. It's a pretty dramatic decline in the zonal winds. So the other thought was that as you warm the northern, you might be wondering, well, what about the rest of the hemisphere? And this is results that we haven't published yet, but we can look at the same change in the zonal winds at 500 millibars over the entire northern hemisphere. And again, the solid line here is the change in the zonal winds, and I've just plotted on here also the change in the sea ice cover, just to not to suggest that they're definitely related, but they're certainly changing at approximately the same rate. And what we see here over the whole northern hemisphere is approximately a 10% decrease in the zonal winds at 500 millibars. So when we have a weaker zonal flow, Rossby theory tells us that we'd expect to see the wave propagation more slowly eastward. So this effect here, we'd expect to cause the Rossby waves to move more slowly eastward. So the other effect is that if you've got a Rossby wave, say a large-scale wave in the 500 millibar flow parked over some region, and you warm the area in the north part of that wave more than the southern part, you'd expect to see the northern part of those waves elongate northward because, of course, those thicknesses are increasing more in the northern part. And this has the effect of making the waves higher amplitude. And we know that, well, before I say that, let's look at this animation that's really quite neat, I think. We're looking down here on the North Pole again, and the red colors are showing where the highest wind speeds are at 500 millibars. And you can see that it's certainly not a simple system. We've got all kinds of little swirls and eddies and places where the winds are strong and places where they're weak. But let's just take a look at how this evolves. This was from the NASA visualization laboratory at Goddard. And so what you can see is that there are periods when the jet stream or the upper level flow is actually relatively zonal, and when that's happening, the waves tend to move quite slowly. quickly. But as the pattern becomes more amplified and the waves become elongated northward, as I just described, you can see that these waves tend to move very slowly across North America. So this is the idea, is that if we're elongating these waves because of enhanced warming in the Arctic, that we should expect to see Rossby waves progressing eastward more slowly. Okay, we've seen that. Go again.
I want to see it again.
You want to see it again? It's very cool. Go for it.
What height is that?
I
Is
think-
that stream more or less?
I think it's 500 millibars, but it might be 300. I'm not sure.
And in meters, more or less?
In meters, well, 500 is about 5,600 meters, more or less. It is very cool. Anybody want to see it one more time, or is that? Okay. So that's the idea. So the question is, is it really happening? And how are we going to figure that out? So the way we came up with was as simple-minded as you could possibly think of, and I like simple, especially when you're talking about such a complicated system as the climate system. So what we did was we took these 500 millibar height fields from the NSEP reanalysis, and we looked for the height range, the range of heights in the 500 millibar field where the gradient is the strongest. And this height, I mean, it's an estimate, and basically all we're trying to do is capture the shape of the flow. So it's really not that sensitive to what exact height you choose. So what you end up with are these data sets, basically, of an isopleph of 500 millibars. And here's an example for this particular day, where we're just trying to capture the shape of this flow and the shape of the waves. And those are all the points on that particular day. This happens to be in November. And in fall and spring, I found that 560 meters plus or minus 50 was a good height to pick to capture that strongest gradient there. In the winter, a little lower, around 5,400, and then in the summer, about 5,700. But it doesn't matter that much which one you choose. So now that we've got these isopleps for every day through the whole NSEP reanalysis, actually we mostly just focused on the satellite record, which is starting around 1979. We can do things like look at, okay, what's the maximum latitude of the ridges? And if you do that, and now this is for the whole hemisphere, not just for this piece of the Earth here. For the whole hemisphere, if you look at how the maximum latitude of the ridges is changing over time, this is what you see. A big increase in the maximum latitude over time, especially starting right about when the ice really started to disappear, right around the early 1990s. So the other thing you can do is look at the difference in latitude between the ridge peaks and the trough bases as an estimate of wave amplitude. And if you look at that over time, again, a lot of interannual variability, but overall there's a increase in the amplitude of the waves, and this is all in autumn still. And the peaks of the ridges appear to be extending farther northward, as we thought they might, and the wave amplitude is apparently increasing. So we can look at this in other ways too. And down here on the bottom here, I've just plotted again the mean 500 millibar height field for the last 12 years in the fall. And you can see that there tends to be a ridge over western Eurasia, a ridge over the Rockies, a trough over the Pacific where the storm track is. So it all makes sense. Now, what we're going to plot here is we can look at just the grid points that are north of 50 north. Okay, so we're just going to draw a circle around 50 north and just count all those grid points that fall north of 50 north as an estimate of the amount of ridging. And if we plot that in a Hofmeiler diagram, this is what it looks like. So on the vertical axis, obviously, is time, and longitude going across the bottom corresponding with the map there, so you can see where this is occurring. And so what we see is that there are these very preferred longitudes where the ridges tend to occur. And it's right where this lines up here in the mean field that I plotted below. We see another ridge over the Rockies, and general lack of ridges basically over the Pacific. Now we can do the same for troughs and look at just points south of 40 South in this case and see where those line up. And again, we see this troughing over the Pacific showing up very clearly, but we also see, interestingly, troughing over the same place that we saw ridging in Western Eurasia. So this suggests that there's a lot of troughing and ridging going on in this part of the world, or a very dynamic area for weather systems. And that kind of goes with what we think of in that area. And again, troughs forming over kind of more east of where the ridges are over North America. So it's interesting that these ridges and troughs tend to align along preferred longitudes. And we know that. They're kind of anchored by the major mountain ranges around the world. So now we want to look at how are these waves changing over time. And here I'm showing you now just a 500 millibar anomaly field for fall instead of just the mean field. And what you can see is there's very clear areas where 500 millibar heights have been increasing lately over most of northern Siberia and also over Greenland. So what we can do now is look at how these numbers of grid points north of 50 north that I showed you a minute ago are changing over time. So the trend in these number of grid points versus longitude. The first thing I want you to notice is the 0 line here. This blue line here is 0. So I think it's amazing that everywhere, just about, the trend is for more ridging at all longitudes. And in particular, these red asterisks are the 90% confidence levels. They're happening very strongly over Greenland and also somewhat over eastern Eurasia. We can do the same for the troughs. And we don't see that they're increasing or decreasing in a sort of general way longitudinally, but we do see a couple areas where there's much less troughing going on over Europe and much less troughing going on over Alaska. And remember that one over Alaska, because that's going to pop up later. We can do the same for this wave amplitude measure. And again, look at where the 0 line is. Just about everywhere in the Northern Hemisphere, this measure of wave amplitude is increasing. And it's not statistically significant everywhere, but it is in a lot of places. So generally, the wave amplitude seems to be increasing all around the Northern Hemisphere in the fall, as we'd expect. So just to summarize this part, we know Arctic amplification is happening. The Arctic is warming faster than the rest of the hemisphere, especially in the fall and winter, and also in the summer, but I'm going to talk about that a little bit later. And this is decreasing the poleward thickness gradient. This has two effects. The first that I've shown you is that the zonal flow at 500 millibars is weakening, and also that the peaks of ridges are elongating northward, and this is increasing the amplitude of the waves at the 500 millibar level. Now both of these should lead to Rossby waves moving more slowly from west to east. We know that from Rossby theory. And that means that weather conditions associated with those waves should be moving more slowly as well. And as I described in the beginning, the kinds of extreme weather that are associated with prolonged weather conditions then should become more probable. Things like drought and prolonged snowfall and cold spells, things like that. So now I'm going to move into the new stuff. And the question, yeah.
Just have a comment.
Sure.
On the previous one. If you imagine that you look at amplitude in terms of this Lagrangian or the displacement of the contour line, but just if you think of it another way, if you think of the perturbation as sort of a wave with sort of a height anomaly, height amplitude, wouldn't you actually get more displacement given the same height anomaly but imposed on a weaker gradient? If you actually have measured wave amplitude as sort of a height anomaly, and you actually impose the height and impose this wave onto a different gradient, then if you have a weaker gradient, the same anomaly will actually give rise to further displacement of the contour. So it seems that if you bring a bit the anomaly as another way, then maybe it's not surprising. So that's surprising that the amplitude that you defined is actually increases when the gradient decreases.
Not sure I caught that
Yeah, okay,
completely,
we
but
can discuss it
we can.
later. Yeah.
Does anybody else catch it?
I think I know what he means. I understand what he means, but it's.
Yeah, so, I mean, but if you think back to the way this was measured, where it's the maximum latitude of, at a particular longitude, and the maximum, or actually minimum latitude at each longitude, then.
Yeah. What I'm saying is that the
Big spread between.
the height perturbation is sort of proportional to the gradient times the displacement. So if you have a lower gradient, then the displacement has to be larger to get the same height perturbation. So that's another way of measuring wave amplitude. So these two way of measuring wave amplitude may not actually give you the same result. So we can discuss it later.
Yeah, we'll definitely talk about that. Okay. So, after all that, the real question is, are the waves really moving more slowly? That's what we think, but is it really? And how do you measure something like that? Because if you take a particular, any old day in January, say, and look at the height field, you kind of go, oh my God, how am I ever going to come up with a way to measure the waves that we're interested in without, getting all messed up and all the other stuff. So this was a challenge I took on recently. And again, I really like to do things simply. So I came up with a simple way, and probably some of the hardcore dynamicists here will laugh me out of the room, but that's fine. I'm going to show you what I did. It seems to be working. So I go back to these isopleths of 500 millibar heights in a very narrow range. And for any given day, I look at the heights that are there, and I take the southernmost grid point at every longitude. Okay, so here's on day one. You can see those little, hopefully you can see the little yellow spots there, which are also grid points of in the same height range, but I'm just taking the southernmost ones of those, and then drawing a line through them and calling that my wave. The next day, you can see that the areas with that same range of height has kind of spread out to the north, and it's not really part of the wave that I'm interested in. The part of the wave I'm interested in is that part below, and that is captured by that southernmost line of grid points there. You can see.
Could you kind of just point where they are, because.
Oh, you can't see the yellow? I'm sorry. I got to change those to pink or something.
So we have a white there.
Yeah, I've got an arrow here too.
Actually, three colors in this.
Yeah, so the yellow is here, kind of bulges up north of the bridge. Here there is almost like a wave-like feature that, or a breaking wave-like feature that extends up to Greenland. Over here, it's going way back over to western Greenland there. So you've got this big excursion of height ranges, or this grid points with this height up north. And you can see that the wave is progressing across the North Atlantic. It's becoming more amplified. As it does so, it actually even looks like it's moving a little more slowly, and then the next day, it continues across the North Atlantic, and then finally, it kind of exits the region. So the idea here then is to take these simplified versions of the isopleth and track the longitude of the peaks in these waves from day to day. And I only take them, the difference from one day to the next, as either -5 degrees of longitude, which would be a westward moving wave, and 10 degrees eastward. So it's confining the wave motion to what you'd expect for a Rossby wave. but it also avoids the problem of having a new wave show up in the region out on the western edge, and so you've got two waves, and then you'd have this big jump, and so I'm just trying to be able to track one wave. Well, nobody's thrown anything at me yet, which is good. All right, so let's look and see how this is panning out. All right, so let's go back to our fall thickness anomalies here again, and look at these different regions around the northern hemisphere, and you can see that, you know, everywhere the warming is largest towards the north. So everywhere we should see some amount of weakening of the thickness gradient, the polar thickness gradient. So what I'm going to do is break this up into regions. We're going to start with the over North America and look at how these wave speeds, as I've measured them, are changing with time. And here's the time series starting 1980 to present, basically, and the blue lines are the individual years, a point for each fall each year, and the dashed line is a 5-year running average. There's a decreased trend with a 95% confidence level over the North American continent. Now over the Atlantic sector here, again, we see a lot of interannual variability, but there's a statistically significant downward trend at the 99% confidence level. Over Europe, very similar looking situation. Now over Asia here, we've got this very strong weakening of the gradient, because not only do we have warming over the Arctic, but we also have cooling over the continent. So you'd expect to see a much more serious slowing down of the waves, and in fact, that's what we see. Over the Pacific sector, same thing, basically, a decrease in the wave speed. So if you put all this together, it paints a picture of decreasing wave speeds. It's a relatively short record, but they're all statistically significant, or reasonably so. And you might be thinking, well, what does that have to do with the AO? Because clearly that should be playing a role here. And I haven't actually done the analysis yet. I just tossed this on here yesterday just to provide at least a visual comparison. But I wouldn't say that any of these curves that I've shown here look a lot like the AO for a fall. And we've got another way of looking at this that we've come up with. And this is a very simple measure of the fraction of the wind at any given place that is in the meridional direction. And all this is, and this was developed by my colleague Steve Vavris, is just the product of the meridional wind speed times its absolute value divided by the total wind speed. So it's really just a measure of the fraction of the meridional wind. Because what we're trying to see is whether there's a tendency for more waviness, and so you should see an increase in the meridional component of the wind. So let's see what this looks like in the fall. First, just the basic measurement here over the whole northern hemisphere. Red values here indicate where the winds are commonly from the south, and the blue areas are where it has a high fraction from the north.
So I don't quite understand how you compute that. Is it an average of daily value, or how do you sort of?
You calculate it at every point over the whole grid, and you just look at the U and V at each point and on every day, and make a calculation of this index.
So you average over every day. So every grid point, the value is just the average over the entire period and done daily.
Well, yeah, it's every day for the whole data record, and then you can average it however you want. In this case, I'm averaging it all over fall. So all the days in every fall for the whole record. But it's a calculation for every grid point on every day. So anyway, this is what it looks like for a typical, well, this is for the whole satellite record, so 1979 to 2011, October, November, December. You see that you tend to get a lot of southerly winds where you'd expect to see them, or near the Aleutian low and also near the Icelandic low, and the northerly components coming down through the middles of the continents. Now, if you take the absolute value of this index, what you get then is an actual measure of where the winds tend to be more meridional and where they tend to be more zonal. So as you'd expect, in the storm track areas where the jet stream tends to reside, the absolute value, or the MCI index, is higher than down in the tropics where the winds tend to be more zonal. So now we can look at is how this absolute value has changed over time and calculate the trends. And that's what's shown on the bottom here. The red areas are where the meridional index has become more positive, so the winds have become more north-south, and the blue areas are where they've become less north-south. The black asterisks are the 99% confidence levels on those trends. And what you can see is a pretty cohesive band stretching around the northern hemisphere. Over North America, there's a large area of increased meridional winds that extends diagonally up across the North Atlantic, across most of Siberia, and into Alaska. But there's also these interesting areas where it's become less meridional, and this kind of goes to what we were talking about earlier, how it appears that the storm tracks are becoming weaker in the Pacific, and I think perhaps the whole jet stream is just moving more northward in this area, and so the troughs, and if you remember back to the trends in the troughs that I said, remember that little bit for Alaska there, the trends were actually negative for the troughs over Alaska. So this is supporting that, showing that I think the troughs are actually moving northward perhaps in that area. And then there's other interesting areas where the winds are also becoming less meridional, perhaps because we know that the jet streams are generally moving northward or poleward because of global warming, and this may be a signature of that. Shift gears now into winter. I can see we're running out of time pretty soon here. So the thickness anomalies in winter look quite different from what they look like in the fall. We have an area over some of the Arctic where they're still very positive and statistically so, significantly so, with a big low that extends down over Greenland. So in this part of the northern hemisphere, we're still seeing what we expect to have a weakened poleward thickness gradient. But over on the Eurasian side and in the Pacific, we have these areas of increased thicknesses down south. And so what we should see over here is actually perhaps not a decrease in the polar thickness gradient. And so it's going to be interesting to see how the wave speeds respond to these different changes in the polar thickness gradient. So we're going to do the same thing. I'm going to walk around the longitudes looking at how the wave speeds are changing. Here, predictably so, maybe, we see again that the wave speeds are decreasing with a lot of interannual variability. Same thing over the Atlantic sector. Same thing over Europe. But when we get over to these other areas where there's warming to the south, we actually see the wave speeds increasing. And it agrees with the thickness patterns that or the thickness anomalies that we're seeing in these areas. So if you put it all together, once again, it's a consistent pattern of wave speeds decreasing where the thicknesses are increasing to the north, and waves actually appear to be increasing in their westward, eastward progression in areas where the warming has been larger to the south. And just to complete that with the AO, again, there's not a lot of visual similarity between the AO and any of these wave speed time series. Okay, so a quick look at the MCI index for wintertime. This looks almost identical to the one for fall. Same areas where you tend to get the strong southerly winds, maybe a little bit farther east in the Atlantic sector. We see the same kind of pattern for the total absolute value of the index. And then the trends are not as consistent, and that kind of goes with the differences in the thickness patterns that I showed you too, where we're not getting the same Arctic-wide increases in the thickness anomaly. So we've got this area over northern, the Atlantic area and also north of Europe, where there's a significant increase in this trend in the meridional component of the wind. Then there are all these other areas where it's actually becoming more zonal. And this whole tropics area where it's also becoming wavier, if you will, according to this index. And so I think this also suggests that the whole jet stream in the winter is moving northward, as others have shown in previous research. But for people working on the tropics, that might be an interesting thing to note. So I'm just going to quickly talk about summer for a minute. It's a very different thing going on in the summertime. Of course, you know, the ice minimum is in the distant past. It's 6 months earlier. So, you know, the ice is not having a direct impact on Arctic amplification in the summertime. But what is having an effect is the dramatic decrease in snow cover in the spring on high latitude land. And this actually was breaking news this week. There was a new study that came out talking about this. And if you look at this trend in the anomalies of the snow cover over northern hemisphere, it's really an amazing trend. And just this past spring, we shattered the record of snow cover on high latitude land as well. It didn't get as much press as the sea ice, but it's there. So the areas that are losing the ice, the snow rather, in the spring are where you'd expect. It's northeastern Eurasia and the northern edges of North America as well. And this lines up pretty well with the surface temperature changes, and that's because when you lose snow on the land in high latitudes in the spring, you're exposing the soil, which is dark, to this very strong spring sunshine. It allows it to dry earlier and warm up earlier. So you're getting, again, this contribution to Arctic amplification because of this extra warming that's happening in the places where the snow is being lost earlier in the spring. So what did the thickness patterns look like in the summer? Well, they're very different, actually. We have, instead of an Arctic sort of center blob like we saw in the fall, it's much more tied to, I think, where these snow areas are being lost, but it's also much more extensive to lower latitudes as well. And there's areas where it's increasing and also areas where it's decreasing. So it's a very different kind of a pattern. And if you look at the height anomalies for the summertime, you see they line up quite well with where these positive thickness anomalies and negative thickness anomalies are, with a big height anomaly over Europe. You can think of the heat waves that they've been having there lately. Height anomalies over the Pacific and also over a lot of the North Atlantic as well. And this lines up with where those thickness anomalies are. So if we look back and do our analysis of the grid points north of 60 north, we had to move north because we're in the summer now, and look at where these ridges tend to occur. They line up mostly over the continents, over Eurasia primarily, and also over North America. They tend to be confined to these longitudes, but certainly not as much as we saw in the fall and the winter. And also note that there's this big increase pretty much across the board in the last few years. And if we look at the trend over time, you can see that there's a large increase in the ridging over Greenland in the summertime. Think of the record melting that occurred in Greenland this summer. This, I think, has certainly been contributing to that. We see actually a decrease in the ridging over Central Eurasia. And if we take a quick look at the troughs as well, the most interesting thing is this big decrease in the troughing over pretty much from Central Eurasia right across the Pacific. And it's a very large area of less troughing. So either the whole thing is moving northward or the pattern of the waves is changing in the summertime. And here are the trends in the meridional circulation index. There are areas where it's definitely showing major increases, like over North America, where we've seen a lot of increase in the droughts and heat waves and forest fires lately. That corresponds, I think, quite nicely with the increases in the meridional component of the wind in these areas, also the North Atlantic, over Russia and that area where they've also had a lot of droughts lately. So I think the summer is a complicated situation though, because the jet stream is a very weak and kind of amorphous entity in the summer, and so it's hard to draw a direct connection between what's happening in the Arctic and what's happening with, say, droughts in mid-latitudes. But clearly we see a big increase in the extreme events in the summertime, and figuring out what's causing that, I think, is a really important question. It's not just happening in the US, but elsewhere as well. And connected to that are, it's not just the ridges, it's also the troughs. We're seeing a lot of wet, cold summers in England lately, and of course that would be connected to an increased ridging over the center of the continent. So there may be a connection there. But I think there's a lot more work to do on that area. And speaking of a lot more work to do, my to-do list is quite long, and I could use some help. So if anybody wants to get involved in this, I would certainly be welcome of that help. One of the first things we want to look at is, what do the models say about this? So far we've been looking at mostly reanalysis information. Can the models look back at time and have the same kinds of relationships that we're seeing in the reanalysis data? Are these past behaviors captured? And as we look forward in the models and look at the projections for the future, as the ice continues to be lost in the Arctic, will these tendencies continue on the trajectories that they're on, or will it level off as the ice basically disappears in the summer, which we're not far from? And I think we talked about this earlier this morning, but there seems to be a lack of theoretical information about just how Rossby waves change in their phase speed relative to the amplitude of the wave. We know a lot about how they respond to the wavelength and how they respond to the speed of the wind, but I haven't been able to find any studies yet that just show how the wave speed changes with amplitude alone, keeping the wavelength constant. So if you know of something like that, please let me know. And of course, the holy grail is to be able to figure out how to predict where these enhanced ridges and troughs are going to be setting up in any given season. And this is what I get asked all the time. Well, what's the weather going to be this winter? And of course, that depends totally on where these ridges and troughs tend to park themselves, or where the slow-moving weather patterns are going to occur. I just got an email from ESPN, of all places, asking what the ski season's going to be like in North America. So, like, how do you answer something like that? Like, I don't know.
You sell your advice, not give it away.
Yeah, I really should. Except then I don't want to stick my neck out yet. But I get that question all the time. But hopefully someday we'll be able to have some probability of where they are likely to set up. And finally, this whole summertime issue, I think, still has a lot of unanswered questions. So just to wrap up, we're living in an unbelievably interesting times. I mean, the monumental change is happening right before our very eyes. I think sea ice is a really clear indicator. It's a great one to use when you talk to the public, because it's something they can look at and just go, holy mackerel, that is really a big, big change in the climate system. You don't have to say very much more about it. But with the change in the Arctic comes, as you've heard, big changes in how the Arctic is being accessed. It used to be that ships just didn't go there. You know, it was just too icy. You couldn't get through reliably. But now they're going through all the time. Not even ships. I mean, last year I think there were 30 yachts that went through the Northwest Passage. And so it doesn't take an ice-strengthened ship anymore. It can be almost anything. In fact, there was a guy who went solo, all by himself without stopping not this past summer, the summer before, solo. And the impact on the living systems up there, I think, are just completely, almost unknown at this point, because as the ice recedes, we're letting light into the Arctic Ocean, and the primary productivity, as shown here, is just blossoming. And of course, this is the base of the food web up there. They're seeing species of fish and different organisms up there that have never been seen before. So the whole system is just changing in amazing ways. But if your eyes are closed, you won't see those changes. And unfortunately, that's kind of where we are right now. So anything you can do to help with that, I think in some ways, because the changes are so large, that people are actually starting to feel the pain and recognize that, okay, yep, things are definitely weird now, and maybe we really should be paying attention to global warming after all. So I hope you have lots of questions, because I'd love to hear them. Thank you.
Any questions for Dr. Francis? Malcolm?
Just that very last comment you made.
About that?
Yes. I mean, I watch this very closely in the news media and in various ways about public perceptions of climate change. And it seems just sort of recently, this, a slow drift towards more acceptance that this is real.
I agree with you.
And so you see people writing as if it is happening rather than speculating. Would you?
I think there has been a bit of a shift, and I think because of
Just maybe the last 12 months.
there's just in the I agree, because the extreme weather has been such headlines, especially in the last few years really, but and stuff like the ice, I mean, that's been getting just unbelievable press this year. And I think people really are starting to, like I said, feel the pain. They're out in the middle of our country dealing with the aftermath of the worst drought we've had since the 30s, and England's just had the worst summer they can remember, or going back as far as they can look, and people are starting to see this weirdness and wonder if actually what we've been saying all along is actually going to be true.
So when you say these monumental changes, we live in interesting times. The interesting seems to be a suitably scientifically neutral thing to say. I mean, when you show those first few slides, I thought it was terrifying.
Well, breathtaking, yeah, that comes to mind.
Well, breathtaking is another neutral term.
So now we can
Okay,
discuss the
terrifying.
other questions for Hannah.
Yeah, terrifying. Yeah, that works for me. Yes.
It's probably very, very true, but I'm interested again in what is the scientifically agreed explanation why the higher latitudes, and it's not just the Arctic, it's the Antarctic too, the higher latitudes in general, right, that are warming faster than the low latitudes. What is
Not Antarctica so much. I mean, the peninsula of Antarctica is warming rapidly, but the rest of it is not particularly.
So it's not true to say that the higher latitudes. are
Right,
warming.
it's not correct.
It's just that the northern hemisphere higher latitudes.
Yes.
That's just a feedback mechanism.
There are a bunch of feedbacks that are contributing to that. The ice itself is probably the first order feedback, and the fact that all this extra energy is going into the ocean and all that heat's being absorbed that would normally not be. The other thing is that there's a lot more water vapor in the atmosphere, which of course is a very good greenhouse gas, and that is contributing to the warming of the surface and contributing to the ice loss, which contributes to the warming, blah, blah, blah. So the other thing I didn't have time to talk about was that I think this tendency to increase the meridional character of the atmosphere is also feeding back to the ice. Especially in the last 6 years, since 2007, we've seen an actual shift in the circulation pattern over the Arctic Ocean, where the high pressure over North America is getting higher, and the low pressure over Siberia is getting lower, which is driving a stronger wind flow from Alaska across the North Pole to the Atlantic side, and blowing a lot more ice out of the Arctic Ocean. So there's a lot of moving parts, but they're all kind of enhancing this positive feedback system.
Yes, Sosha.
Question about predicting the future weather. I'm wondering if it wouldn't be possible to recreate some sort of historical record of those extreme events from, say, various media, mostly probably from papers back in the day, and comparing them with the patterns, these amplitudes that you were showing on the maps, the troughs and the ridges, and to see whether there would be any significant linkages to these extreme weather events, to be able to then develop a tool that predicts, in some ways, weathers? Is it totally ridiculous to do that?
Doesn't sound ridiculous to me. It sounds like a lot of work.
It sounds like a lot of work, but it might be very useful.
but-
Although I'm sure that the past records are very scarce. Right now we have so much information with the internet and all, but
You can go back actually to the late 40s pretty easily, because there's actually a tool online. You remember those little plots I showed of the wettest days in Chicago and the
Yes,
coldest days in Florida, that sort of thing.
exactly, right.
There's actually an online tool that you can go in and say, show me the you know, whatever you want to pick. You know, it can be a precipitation event or a temperature event, and it'll pull up however many of the worst in that particular area is. And then once you know what those days are, then you can go back to the whatever analysis you want to look at, 500 millibars or surface pressures or whatever, and see what the patterns were on those days. And that's how I created those.
Where's
little,
that tool located?
Oh, God, it's so buried in NCEP's website. I'd have to dig it up for you and send it to you, because I
I know where
can't
you
tell you right off
deposit,
the
but I
top
don't
of
know
my
where-
head.
I know
It's a
where you-
wicked cool tool, though.
Yeah, that sounds really nice.
It is.
Oh, yes, Diego.
I have a question about the methodology you used in order to measure ridging based on counting the number of grid points. So I think it's related to what Edmund was saying. So structurally, you might be seeing different things, because if if everything's getting warmer, then your heights are changing, and you're not specifying a range. Structurally, they might be different, because at first you're maximizing the gradient, right? The height gradient, and that's your criterion for getting the
selecting.
range. And maybe later on, that structurally might be different, and also, and that might account for some region. But also, there's another thing, which is the change in the gradient. So if you see the graph where you show the actual grid points,
Right.
in the trough, you see that it's much thicker than the ridge.
Right,
so
right, right.
only the change in gradient, because you're seeing different things maybe.
Yeah, that's true.
The change of gradient might account for
Some of that, for sure.
some of that
Right.
change in counting, and maybe that's because of geometry that might not reflect the same way when in a ridge than in a trough. So that might account also for
Yeah.
maybe you see more troughing and not structurally. Maybe it's not happening structurally, and it's only you're seeing something structurally different, and there's a difference in gradient, which gives you more
I got you.
thickness.
Yep.
So is there any way in which you could separate those, maybe those effects from actual ridging and troughing?
Yeah. Well, the maximum and minimum
Yeah,
wouldn't be
yeah.
affected by that too much, but
Yeah.
I understand what you're saying about the numbers of grid points above a
Exactly.
certain latitude or something like that. Yeah, I'd have to give that some thought, see if we could separate that out somehow. You know, maybe take just one point at each longitude or
Yeah,
something like
exactly.
that, instead of the whole mass. That's good. Good thought.
Edmund, do you have a question?
Yeah, I also have a question. I have a question about the speed, how you estimate the speed. It seems to me that if you just look at where the ridges are, wouldn't that be at any time, so wouldn't that be sort of strongly affected by this sort of transient weather system, troughs and ridges that are more mobile and shorter wavelength, and then I'm sort of surprised that you get a speed of maybe 2 to 3 degrees per day, because you didn't really do anything to
Well,
filter
I
those
did, I
things
forgot to
out.
mention, I did smooth
Okay,
those
so
curves.
actually you smooth
There
those
is,
curves,
and
yeah.
I forget whether I took plus or minus,
Yeah, okay.
I think it was like a 5-point smoother or something like that, so 5 longitude smoother. I know I smoothed it. I can't
Yeah,
remember
okay.
exactly how much, but that would eliminate.
Are you using NCEP reanalysis or?
Yes.
Okay.
Yeah,
that's-
so I
that's
did
like 12
smooth
and a half
it, and
degrees.
that got rid of the transient waves.
So that's probably where that's about.
Yeah.
If you don't smooth, then. it
Right,
would
I
be
forgot to
surprising.
mention that, yeah, otherwise you'd get some, yeah.
So there is another question, Mingwa? Yeah.
Yes,
I have a question. The extension of the ridge to high latitude and the happening of the decreasing of ice, are they happening at the same time? I mean, are they happening at the same time, or there's a lag between them?
Well, certainly the overall tendencies are happening at about the same time. I haven't actually looked to see whether any particular year is corresponding to a particular increase in ridging at, some location. But the trends overall are, ice is doing this and the ridges are doing that. But they do seem to coincide in time pretty well. Right when the ice really started to disappear rapidly in the early 90s after that the period of high AO indices, seems to be when the ridges really started to extend northward. So I can't say for sure whether that was a cause and effect thing, but it's coincidental.
It's difficult to give a causal relationship between them. It's very difficult to say the ice decreasing affects the extreme.
Well, that's what I tried to show with the thickness anomalies and the fact that it's warming more to the north. And so that would, if you think about what would happen to the northern parts of those ridges, is those heights are going to increase because the thicknesses are increasing. So that means that if you take the same height value, you're going to have to go farther north to find that same range of 500 millibar heights because of the increasing thicknesses. So I think there actually is a plausible mechanism there.
Just another question. Modern commercial aviation, navigation now is so accurate that airlines typically predict the transit time, say from New York to London or Madrid, within minutes. Now, is it anecdotal information coming from pilots or recorded that may help, add some information about the changes in the jet stream, or are the pilots clever enough to avoid adverse winds to get there as soon as possible? That would mess it all up.
Oh, they have whole systems that allow them to avoid, when they're going against the jet stream, to not get into the core of it, and to ride it when they're going with it.
So it sounds like it would be a reliable source of information.
But going into Europe, it would maybe, because they want to be in that jet stream, right?
Right. Yeah. So they want to be in it going
Right.
east and then not in it coming
If
west.
you go on a program like flightaware.com, you can track a given flight minute by minute
Yeah.
across the Atlantic.
Yeah, I don't know. Jet engines have changed and jet body shapes have changed. I don't know whether that would be a reliable resource or not, and how much it could tell you. But you'd think it might show up in something like that. I don't know.
The aircraft is measure winds, and those winds get into the analysis. So,
Yeah.
So it's in there.
Yeah, winds
Yeah.
measured by aircraft are in there.
Yeah.
It's a bit like in oceanography. Scientists rely on anecdotal information from fishermen about whether fish are or they're not. And I'm just wondering whether pilots flying across the Atlantic every few days for 30 years would have any sense.
Yeah. Well, like Evan said, the winds they measure are definitely going into the reanalyses and the weather forecasts and all that. So, but I don't know whether there's been any attempt to measure changes in the transit times across the Atlantic or something like that.
So there are no more questions, so let us thank Professor.